Let's talk about similarity, correlation, and entropy as it pertains to voice over IP security. We're talking about data mining. We have a data set. We've used sensors or some sort of form of data ingestion method. We have the data. Now, how do we mine it and use similarity, correlation, and entropy and really understand these concepts to help us in voice over IP security? That is the goal of this exercise here. The first thing that we want to go over is why. Why these three? Why similarity, correlation, and entropy? What do they give us that's going to make it worth our while as data miners? And then we'll go over similarity, we'll go over correlation, we'll go over entropy, and then we'll put it all together. The voice over IP attack detection, and where the heck does this apply? And how can we apply this? And then we'll go over a quick summary. Let's talk about why similarity, correlation, and entropy. Similarity helps us with figuring out if two call flows are suspiciously alike. We can do clustering or we can do replay detection. That similarity helps us when we compute similarity from even a math level, and we're gonna go over the mathematics. We can figure out if two call flows are suspiciously alike. Like this is some sort of bot that's replaying a call flow. And then we have correlation. Check if expected relationships holds. Call duration, RTP packets, right? When these correlations break, it signals anomalies or attacks. We're looking at SIP floods. Correlation now exposes hidden attack patterns by revealing when VoIP traffic behaves unnaturally. Again, this goes along with attack flows. These are things that are anomalous in nature. We're not looking for the normal behavior, we're looking for the anomalous behavior. And so similarity, we were looking at how similar things were. The opposite is distance, figuring out how far, computing the Minkowski or the Minkowski distance, however you say that name. In similarity, we're trying to see how similar, how closely related these data points are. Correlation is checking if expected relationships hold. We're trying to expose the hidden attack patterns by revealing VoIP traffic that's behaving unnaturally. Entropy, we're looking at how uncertain or structured is a stream of data. We're looking at the natural way people talk isn't very scripted. It has a lot of differentiation, a lot of uniqueness, and a bot would be very rigid and scripted. And so we're going to apply these from the voice over IP lens that I want to do this exercise in. We're going to apply these to SIP signaling, the invite and register, RTP media, the different RTP, the media packets, and per flow stats, packets per second, bytes per second, duration, etc. And quick review of SIP signaling essentials. Session initiation protocol establishes, modifies, and terminates voice over IP calls. So we have register, invite, trying, ringing, OK, the acknowledgement, and then bye. And so these are the SIP signals that we're going to be looking at when we get VoIP data. Maybe we're using Wireshark and we're able to see SIP signals, and we're able to see the register, the invite, these different signals. And then we can take that data and then we can use that to compute similarity. We can compute correlation. We can compute entropy. And we can see the actual human speech. We're going to be looking at RTP data. But with SIP signals, we'll be looking at how the calls are orchestrated. And we can see if we can do some analysis on it and see if things are scripted, bot-like, or if it's genuine humans. And this could help us figure out about SIP floods and other attacks that would either overwhelm the network with a distributed denial of service, or is doing something malevolent, toll fraud, and trying to cost the business more money or the individual more money. There's a variety of different attacks that we can look at, and we can use this data for that purpose. And another example is register invite patterns can be correlated with success, failure, outcomes. Entropy of headers help distinguish humans versus scripted bots. Let's go over the correlation formula, and this is the Pearson version. It's the sum of minus the mean of data point X or data X, data set X, and then yi minus the mean of Y data set divided by the square root of the sum of X, and then times the sum of yi minus the mean of Y squared. So you sum all those up, you multiply them, you do the square root, and then you use that as your divisor for the Pearson. And so here we have the Spearman, and then where DI is the difference between ranks. Spearman deals with rank. Entropy, we have the entropy formula. And so this is just a summary of the formulas. This gives a high-level view of what we'll be going over. And then we have similarity, which we have the cosine similarity and the Jacquard similarity. We have magnitude down there, and then we also have some set notation, intersection, and union. Similarity concepts, that's what we'll first go over. We have the cosine similarity, which is the vector angle. The cosine similarity of A and set A and B is A dot product with B, and then divided by the magnitude of A and the magnitude of B multiplied together. Jacquard similarity deals with sets and Boolean overlap. And so we're going to be using set notation here. Cosine similarity versus Jacquard similarity. Cosine similarity measures the angle between two vectors. It's best for frequency-based data. We're talking about numeric data most of the time here. SIP header counts, RTP packet size histograms, right? And then we have Jacquard similarity, which measures the overlap between two sets. Values range from 0 to 1. It's best for binary or Boolean features, 0 or 1. You have something, you don't have something, presence of something or not presence of something. Cosine cares about the direction and proportion, and then Jacquard cares about just shared membership. And so this is a visual example of cosine similarity. Treats SIP header counts as vectors. We have vector A, 2103, and then vector B, which is double of A. We see that they're going in the same direction, but B is twice as long. In Jacquard similarity, we treat SIP headers as sets. A as a set, as invite via and from, B has invite via contact. They have two that are similar. They both share invite and via. The Jacquard similarity is there's 4 different types of attributes, and 2 of them are shared. 2 out of 4. 0.5 is the Jacquard similarity of that problem. This is another visual example of non-collinear cosine similarity in a different Jacquard similarity. Here we have 2, 1, and then we have 1, 2. So they're non-collinear, and then we can find the angle of that by doing the formula from before. The dot product of A and B divided by the magnitude of A and the magnitude of B square rooted, or I'm sorry, not square rooted. Let's go back here. Not square, just the magnitude, which is the formula has the square root here. Cosine similarity. We take the square root of 5 and 5. 2 squared, yeah, that would make sense. And then the Jacquard similarity has the invite via from root for set A, and set B is invite via contact. There's 1, 2, 3, 4, 5 different possibilities, but 2 of them, invite and via, are both shared. Here's a more math-related example. We have the cosine similarity. You take the square root for the magnitude of A. It's the square root of each of your attributes added together that are all squared. This is a more math-related example that you can see it more straightforward. And again, this is showing us, measures the angle between two vectors. That's what this is doing. It's values from 0, orthogonal, meaning they're perpendicular, to 1, identical. And we saw that this one was identical direction. Now, this one isn't quite orthogonal, but then here we have this one is nearly identical. Direction is very similar because it's almost 1. And then we have Jacquard similarity. We have invite to, from, call ID, and via for A. And then we have B, invite to, from, call ID, via contact. And so we take the intersection of that, of A and B. The intersection will be, okay, they have invite, they have to, they have from, they have call ID, and they have via. There's 5. And then the union of is taking all of them together is 6. We get 5 divided by 6. B is a superset of A. Feature vectors, these are some examples. And the use cases really is what I want to bring this back. Replay and clone detection, high pairwise similarity across many from multiple IPs, bot family clustering. These are things that we're trying to find. All right, I'll stop there and I'll go on to correlation for the next ones. Thank you. I'll see you later.